The Apollo astronauts lied to us. Not about the science, not about the moon. They lied about what was actually up there. For decades, the men who orbited and walked on the lunar surface came home and described, in careful, measured, military pilot language, a gray, dead world, a museum piece, geologically simple, thoroughly understood. The data backed them up. Thousands of photographs, spectral analyses, topographic scans, all of it pointing to the same conclusion. The moon is a quiet, predictable place where nothing has happened in 3 billion years, and nothing will happen for 3 billion more. They weren't lying on purpose. They were repeating what their instruments told them. What the culture of the program expected them to say. What 50 years of robotic orbiters seemed to confirm. The story was internally consistent, scientifically defensible, and deeply structurally wrong. Because on April 6, 2026, 4 astronauts flew within 4,000 miles of the surface aboard the Orion spacecraft, and immediately started seeing things that didn't match, colors that shouldn't have been there, topography that photographs had completely failed to convey, flashes of light on the darkened surface that made scientists in Houston literally scream with excitement, and a bright swirling pattern visible from Earth with a backyard telescope that, after 4 centuries of observation, still has no confirmed explanation. The Artemis II crew didn't just fly around the moon. They caught it in a lie that every previous mission had missed. And what they found changes everything we thought we knew about the most familiar object in our sky. Think about what it means to stare at something for 4 centuries and still not understand it. From the moment Galileo pointed his crude telescope at the lunar surface in 1609 and sketched the dark plains he called mare, seas, humanity has been accumulating data about the moon with increasing precision and decreasing humility. We mapped it. We photographed it. We sent probes crashing into it, orbiting it, soft landing on it. 12 human beings walked across its surface and brought home 842 pounds of rock. We built computer models of its interior, its history, its geological evolution. We named every significant crater, ridge, and basin. We created atlases of its chemistry and mineralogy precise enough to identify individual rock types from orbit. And we told ourselves we understood it. That was the lie. Not a malicious one. Not even a conscious one. It was the lie of premature certainty, the very human tendency to mistake a complete map for a complete understanding. The moon appeared to be the simplest large object in the solar system, 4.5 billion years old, geologically dead for 3 billion years. No atmosphere, no weather, no plate tectonics, no liquid water. Just a frozen record of the solar system's early violence, sitting 240,000 miles away like a museum exhibit behind glass. Informative, inert, known. The Artemis II mission did not go to the moon to overturn this understanding. It went to refine it, to fill in gaps, to collect human eye observations that robotic systems cannot replicate. The science team did not expect to be surprised. They expected to confirm, to elaborate, to add nuance to a picture they already thought they understood. Instead, they got 7 hours of consecutive surprises. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen spent those 7 hours circling the moon aboard the Orion spacecraft, christened Integrity by the crew, a name chosen with deliberate intention. They carried a fleet of Nikon Z9 cameras, optical filters calibrated for lunar geology, a set of eclipse glasses, and roughly 2 years of intensive geological training, courtesy of David Kring, a planetary scientist at the Lunar and Planetary Institute, who had spent decades studying the lunar surface from photographs and had prepared the crew to look at it in a fundamentally different way. Kring's preparation process was itself a remarkable undertaking. He didn't simply teach the crew geological terminology. He taught them to see to recognize the subtle color shifts that distinguish pyroclastic glass from anorthosite, to read the angle of a shadow and extract topographic information, to notice when a surface feature doesn't fit the pattern it should fit. He spent months transforming skilled test pilots and mission specialists into field geologists, then sent them 240,000 miles away to do fieldwork through a window. The distinction between what a camera sees and what a trained human brain perceives turned out to matter enormously. A camera records reflected light at fixed wavelengths. It captures brightness values within the limits of its sensor. It cannot compare what it's seeing now to what it saw 10 minutes ago from a slightly different angle. It cannot register the cognitive dissonance of a color that doesn't belong, the nagging sense that a shadow is falling in the wrong direction, the sudden recognition of a pattern that no flat photograph prepared you for. A brain connected to eyes that have spent months learning to read lunar geology does all of those things simultaneously, automatically, without being asked. The crew worked in shifts. Because window space in the Orion capsule is limited, only 2 astronauts could observe at a time. So they rotated in pairs, each team taking between 55 and 85 minutes at the windows before swapping with the other pair who had been exercising or tending to mission tasks. They used camera shrouds, essentially black curtains with apertures cut for the lenses, to prevent cabin light from reflecting off the window panes and contaminating their photographs. The shrouds were unglamorous, itchy, slightly ridiculous pieces of equipment. They were also absolutely critical. Without them, every photograph would have been compromised by internal reflections. With them, the crew produced some of the highest quality close-range lunar imagery ever captured by human hands. It was meticulous, methodical, unglamorous work. The kind of science that never makes the inspirational highlight reel, but determines whether the data is actually usable. One of the first major targets on their observation list was the Orientale Basin. If you haven't heard of it, that's because it sits right on the boundary between the near side and the far side of the Moon, in a position where it's nearly impossible to see clearly from Earth, and where Apollo astronauts caught only fragmentary glimpses of its outer edges. No human being had ever observed the full structure. No human eye had ever taken in its complete geometry from a position close enough for it to register as something other than a diagram on a screen. Orientale is nearly 600 miles across. It formed approximately 3.8 billion years ago when something massive, likely an asteroid several dozen kilometers wide, slammed into the lunar surface with enough energy to instantly liquefy rock hundreds of kilometers deep. The impact punched completely through the outer crust and created a multi-ring impact basin so geometrically precise that scientists have compared it to a target on a firing range pressed into stone. From orbit, the concentric mountain rings look like a bull's eye drawn by a compass the size of a small country. The innermost ring rises to elevations that rival the Himalayas. The outermost ring extends to diameters that would span from New York to Chicago. Wiseman described the innermost ring, the tight annular structure that defines the basin's core, as looking like a pair of lips or a kiss pressed into the far side of the Moon. Then he paused, corrected himself. It was far more circular than he had expected from training images. The northern section was wider and darker. The southern section was lighter and more sharply defined. The proportions, the symmetry, the sheer overwhelming scale of it. None of it had translated properly from flat photographs into three-dimensional reality seen through a window at 4,000 miles. This was a recurring problem throughout the flyby. Not a problem in the sense of a malfunction, a problem in the sense that the world kept refusing to match the model. Hansen, the Canadian astronaut, put it most directly in his post-mission debriefing. The thing that shocked him most was the three-dimensionality of the Moon. On paper, on screens, in every simulation and training exercise they had completed, the surface looked like what it technically is, a sphere covered in craters. In person, from the vantage point of a spacecraft moving through lunar space, the elevation changes arrived in the mind with a physical impact that no amount of preparation had fully conveyed. Kring, listening from the science evaluation room at Johnson Space Center, had been trying to communicate this exact point for years. The elevation differences near the moon's south pole are greater than the height of Mount Everest above sea level, but seen from orbital photographs, they register as subtle shading variations. He could hear Victor Glover finally understanding it, could hear the quality of his observations shift from description to genuine comprehension. Something was clicking into place that years of screen-based training had not been able to install. Glover, for his part, couldn't stop talking about the Terminator. Not the science fiction franchise, the Terminator line. The boundary dividing the illuminated half of the moon from the half in shadow. The precise edge where lunar day meets lunar night. Along that line, sunlight arrives at such a low grazing angle that every surface feature casts a shadow 10 or 20 times its own height. A boulder the size of a car casts a shadow the length of a city block. A ridge 100 feet tall casts a darkness that stretches for miles. The terrain becomes a landscape of extreme contrasts. Islands of blazing white rock surrounded by voids of absolute black. Craters whose rims catch full sunlight while their floors have been in perpetual darkness for billions of years. Glover called it the most rugged thing I have ever seen from a lighting perspective. He described islands of light surrounded by valleys that looked like holes cut in the universe. Pockets of terrain so profoundly shadowed that they appeared to be simply missing from the surface, as though someone had taken scissors to the moon and cut out irregular pieces and left nothing behind. Kelsey Young, the mission's lunar science lead at Johnson Space Center, told him afterward that those observations, the specific way he described the interplay of light and depth and structure, were precisely the kind of thing that human observational capacity contributes to science that no autonomous camera system can replicate on its own. The comparison, the interpretation, the immediate recognition of anomaly, these are not algorithmic processes. They are things brains do. Young explained the optical dynamic with a simple analogy. Shine a flashlight directly down onto a sandbox from directly above, and you'll see color, the tan of the sand, any variations in mineral content, any stains or deposits. Move the flashlight to the side until it's nearly horizontal, and the color disappears entirely. But now you can see every ridge, every ripple, every grain boundary in the surface. The Artemis II crew watched both effects unfold in sequence as their spacecraft moved through its flyby arc, seeing the same geological formations first under high-angle, direct illumination, revealing color and chemistry, and then under low-angle grazing illumination, revealing topography and texture. It was a form of simultaneous geochemical and structural analysis that no stationary orbiter had ever been positioned to perform. The colors they reported were not what anyone expected. The crew described shades of brown and green on the near side, distinct color variations across crater walls and lava plains that had appeared essentially uniform in orbital photography. These variations correspond directly to mineral composition. Iron-rich basalts produce different reflectance signatures than calcium-rich anorthosites. Titanium deposits shift the apparent color of the regolith in ways that orbital spectrometers can detect statistically, but cannot resolve at the granularity of individual geological units. The astronauts were performing geological fieldwork from 4,000 miles away, identifying mineral boundaries that orbital data had suggested, but never confirmed at this level of spatial resolution. The implications are not merely academic. Mineral composition maps of the lunar surface are critical for planning resource extraction operations. If NASA intends to establish a permanent presence on the moon, which is the stated goal of the Artemis program, then knowing precisely where iron oxide, titanium ilmenite, and water ice are concentrated is not a scientific curiosity. It is engineering intelligence. It determines where you dig, where you build, where you send crews to collect raw materials for life support systems and rocket propellant. Then there was Reiner Gamma. Reiner Gamma is one of the strangest surface features on any body in the solar system, and it sits right there on the near side of the moon, visible from Earth through a decent telescope, waiting to be explained for 400 years. It occupies a region of Oceanus Procellarum, the ocean of storms, a sprawling dark basaltic plain on the western edge of the lunar near side. The feature itself is a bright, swirling pattern spread across roughly 60 kilometers of otherwise unremarkable dark surface. No topography, no relief, no shadow, no rim, no ejecta rays. It simply sits there, luminous and inexplicable, looking like a thumbprint left in the dust by something immeasurably large. First observed through primitive optical telescopes in the early 1600s, Reiner Gamma was initially catalogued as a crater, a reasonable assumption given that most bright features on the moon are crater rims or fresh impact ejecta. But as telescope technology improved through the 17th and 18th centuries, observers began to notice something unsettling. The bright feature cast no shadow. It had no raised rim. It showed no topographic expression whatsoever. Under every angle of illumination, at every phase of the lunar cycle, Reiner Gamma remained flat. The brightness was not a physical structure. It was something painted onto the surface, a pattern of reflectivity that existed without any corresponding physical form. Modern orbital mapping confirmed what naked-eye observers had suspected for centuries. Reiner Gamma is a purely albedo feature, a region where the surface reflects more light than its surroundings, but where the physical terrain is identical to the dark basalt plains around it. The swirl pattern is not a deposit of different material laid on top. It is not a remnant of a volcanic eruption. It is not a flow feature or a weathering artifact or a trick of light. It is something the surface itself has become, chemically brightened in a complex swirling pattern, without any obvious mechanism to explain why. What makes Reiner Gamma genuinely, deeply strange is what sits beneath it. Directly below the swirl, embedded in the lunar crust, is a powerful magnetic anomaly, a concentration of magnetized rock generating a localized magnetic field strong enough to form a miniature magnetosphere stretching approximately 360 kilometers across the surface. To understand why this is remarkable, you need to understand that the moon has no global magnetic field. It lost that approximately 3 billion years ago when its small iron core finished cooling and its internal dynamo shut down. Without a functioning dynamo, the moon cannot sustain the planet-scale magnetic field that protects Earth from solar radiation and deflects the constant stream of charged particles that streams outward from the sun. But scattered across the lunar crust, there are remnants, fossil magnetic fields, locked into rock that solidified during the brief window when the moon's dynamo was still functioning, and then preserved in crystalline form as the rock cooled. These crustal magnetic anomalies are distributed asymmetrically across the moon, concentrated primarily on the far side and in specific geological provinces on the near side. Most are weak. A few are strong. Reiner Gamma sits above one of the strongest. The leading theory for how the swirl formed is called the solar wind shielding hypothesis. The solar wind, that constant accelerating stream of charged protons and electrons that flows outward from the sun at roughly 400 kilometers per second, chemically alters the lunar surface through a process called space weathering. Over hundreds of millions of years, bombardment by solar wind particles breaks molecular bonds in the surface minerals, deposits nanophase iron particles, and progressively darkens the exposed regolith. Soil that has been exposed to solar wind for 1 billion years is measurably darker than fresh soil from a recent impact crater. Where the localized magnetic field above Reiner Gamma deflects incoming solar wind particles, the surface beneath is partly shielded from this darkening process. The soil there stays brighter. Where the field has gaps, or where its geometry creates cusps and edges, solar wind particles concentrate and accelerate, darkening the soil even faster than average. The result is a pattern of bright and dark lanes that traces the three-dimensional shape of the magnetic field, projected down onto the flat surface, like a tan line on skin left by a piece of fabric cut in an unusual shape. It's an elegant explanation, and it doesn't fully work. The magnetic anomaly below Reiner Gamma doesn't align cleanly with the geological structures around it. Many other lunar swirls are found on the exact antipodal point, the opposite side of the globe, from major impact basins, suggesting that the shock waves from large impacts can magnetize crust as they travel through the lunar interior. But Reiner Gamma has no obvious antipodal impact basin. One hypothesis proposes that a cometary nucleus struck the surface and magnetized it during the collision, a highly speculative mechanism with no direct evidence. Another theory suggests a buried, uniformly magnetized elliptical disk beneath the surface, possibly deposited by an extremely oblique grazing impact that skimmed across the surface at a shallow angle and left a magnetized slab instead of a conventional circular crater. A third hypothesis proposes that fine dust particles electrostatically lofted by micrometeorite impacts were sorted by the local magnetic field into the bright swirl pattern over geological timescales. None of these hypotheses have been confirmed. None have been ruled out. After 4 centuries of observation and 50 years of orbital analysis, Reiner Gamma remains an open problem, which is to say, one of the most visible features on the Moon is something we fundamentally do not understand. A future mission called Lunar Vertex, led by the Johns Hopkins Applied Physics Laboratory, is currently being developed with the specific intent of landing directly on Reiner Gamma and driving a rover across it to measure magnetic field strength and orientation at ground level, sample the soil chemistry in bright and dark lanes, and test the solar windshielding hypothesis directly. Until that mission flies, Reiner Gamma is a standing rebuke to the assumption of lunar simplicity. The Artemis II crew observed it during their near-side pass, documenting its brightness against the surrounding mare and capturing color gradient observations that will be compared against orbital spectral data to see whether human visual discrimination reveals boundaries or transitions that automated instruments missed. Halfway through the flyby arc, the Moon passed between the spacecraft and the Sun. From the crew's perspective, having traveled to a point 4,000 miles beyond the lunar limb, the Sun slipped behind the disk of the Moon and disappeared. The corona, the Sun's outermost atmosphere, bloomed around the Moon's edge in a ring of ghostly structured light. Streamers extended outward tens of millions of miles. Loops and plumes of magnetized plasma caught the geometry of the Sun's global magnetic field and made it visible. The solar corona, normally invisible except during the brief, rare alignment of a total solar eclipse, was unveiled in its full, unfiltered complexity. From Earth, a total solar eclipse lasts a few minutes at most, because the angular sizes of the Moon and Sun, as seen from our planet's surface, are almost exactly equal. A cosmic coincidence so improbable that it seems designed, which is perhaps why so many civilizations across history interpreted it as precisely that. From 4,000 miles behind the Moon, the geometry changes dramatically. The Moon subtends a larger angle than the Sun. The lunar disk is big enough to completely block the solar disk with room to spare. And the spacecraft was moving at a velocity that kept it behind the Moon's shadow for nearly 54 minutes, almost a full hour of totality. No human being had ever experienced a solar eclipse from this vantage point. No human being had ever watched the corona for nearly an hour from a position beyond the Moon. The crew put on eclipse glasses during the partial phases, becoming the first people to use eclipse viewers at the moon. When totality began, they removed the glasses and looked directly at the scene. Wiseman called it an absolutely spectacular, magnificent experience. The understatement of geological proportions. Stars appeared: Venus, Mars, Saturn, Mercury, all visible in a sky that was no longer washed out by the sun's overwhelming brightness. Earth hung in the field of view, illuminated by full sunlight, a small blue and white disk against the darkness. The corona itself was far more complex and structured than any photograph had conveyed. A dynamic, three-dimensional architecture of plasma and magnetic fields that the crew described in terms that researchers are still working to catalog and quantify. NASA's science team is still analyzing the photographs taken during totality. The initial assumption was that the glowing halo around the lunar disk was entirely the solar corona, the outer solar atmosphere. But preliminary analysis suggests the images may include a significant contribution from zodiacal light, the faint diffuse glow caused by sunlight scattering off interplanetary dust distributed along the plane of the solar system. Distinguishing between coronal structure and zodiacal light contribution from these images could provide new measurements of dust density and distribution in the inner solar system. Measurements that are extraordinarily difficult to make from Earth's surface, where atmospheric scattering contaminates the data. Glover, attempting to describe the solar streamers extending from the corona, compared them to the spotlight beam from the top of the Luxor Hotel in Las Vegas. Then he took it back. "This looks like what that wants to be when it grows up," he said. "Something that has heard about Las Vegas and aspires to that level of excess, but has the raw materials of a star to work with." And then, in the darkness, the moon started flashing. 6 times during the 54-minute eclipse window, the crew saw brief, brilliant points of white to bluish-white light appear on the darkened lunar surface. Each flash lasted less than a millisecond, as fast as a camera shutter, opening and closing. Wiseman described them as pinpoints of intense white light that appeared without warning and vanished instantaneously, leaving no persistent glow, no aftermath, no visible crater. They were meteoroid impacts, small rocks, larger than dust, smaller than a boulder, somewhere in the centimeter to decimeter size range, slamming into the airless lunar surface at velocities between 20,000 and 70,000 miles per hour, and vaporizing on contact in a plasma flash. On Earth, objects in this size range burn up in the atmosphere at altitudes between 50 and 80 kilometers, converted into the streaks of light we call shooting stars. The thermal energy of deceleration vaporizes them before they reach the ground. The atmosphere is not just a life support system. It is a debris shield, filtering out hundreds of thousands of projectiles per day that would otherwise pepper the surface. The moon has no atmosphere, nothing to slow incoming debris. Every particle that approaches the lunar surface arrives at full cosmic velocity and leaves a permanent scar. The surface of the moon is, at the microscopic scale, a record of every impact it has ever experienced. A text written in craters, from basin-scale scars hundreds of miles across, down to microscopic glass spherules formed by the vaporization of single dust grains. In the science evaluation room at Johnson Space Center in Houston, the reaction to the impact observations was visceral. Kelsey Young reported audible screams of delight from the scientists monitoring the crew's real-time observations. Not polite scientific enthusiasm, but the raw, involuntary reaction of people witnessing something unexpected. The crew had been briefed that they might see impact flashes during the eclipse, given that the darkened surface would make any luminous event visible. The expectation was perhaps 1 flash, 2 if conditions were favorable. 6 in a single observation window was extraordinary, a statistical event that tells scientists something meaningful about the current flux of impactors in the lunar environment. Jenny Gibbons, the mission's backup astronaut, told reporters afterward that impact flashes are something we have not witnessed often, and that the number of confirmed sightings was outstanding for a single observation window. The practical implications extend far beyond scientific curiosity. If NASA intends to build a permanent crewed base on the lunar surface, which is explicitly the stated goal of the Artemis program, then the frequency, size distribution, and geographic variation of incoming impactors matters in the most immediate engineering sense. A rock the size of a large marble traveling at 40,000 miles per hour carries kinetic energy equivalent to a hand grenade. A rock the size of a tennis ball at the same velocity is comparable to an artillery shell. Habitat walls, solar panels, communication antennas, pressurized rovers, EVA suits, all of these systems have finite impact resistance. All of them are vulnerable in ways that atmospheric shielding makes largely theoretical on Earth and completely real on the Moon. Peter Schultz, a professor of geological sciences at Brown University who has spent decades studying hypervelocity impact physics, stated after the mission that the Artemis II observations demonstrate that the daily flux of small impactors should be monitored much more comprehensively before any permanent crewed installation is established on the lunar surface. This is not an argument against lunar bases. It is an argument for understanding the threat environment before you build inside it. NASA's ground teams are now correlating the crew's visual observations with data from the Lunar Reconnaissance Orbiter, which was conducting its own observations from a 100-kilometer polar orbit during the same window. Before launch, NASA had invited citizen scientists worldwide to monitor the Moon with backyard telescopes and independently record any visible impact flashes, specifically so that ground-based observations could be matched against the crew's visual reports for cross-validation. The resulting dataset, human eyes at 4,000 miles, LRO cameras at 62 miles, amateur telescopes at 240,000 miles, represents the most comprehensive simultaneous characterization of lunar impact activity ever assembled from a single observation window. The crew also dedicated significant observation time to the South Polar region. This matters because the South Pole is where NASA plans to land astronauts on future Artemis missions, specifically Artemis III and subsequent crewed surface operations. The region contains some of the most scientifically valuable terrain on the Moon, the permanently shadowed interiors of polar craters, where temperatures have never risen above -250 degrees Fahrenheit, and where water ice deposited by billions of years of cometary and meteoritic bombardment may be preserved in extractable concentrations. Ice that could be processed into drinking water, breathable oxygen, and rocket propellant, potentially enabling a sustained human presence without constant expensive resupply from Earth. But the South Pole is also profoundly more challenging terrain than the equatorial regions where Apollo astronauts landed in the late 1960s and early 1970s. The Apollo sites were selected partly for safety, flat, open-air plains where lighting was predictable and terrain hazards were minimal. The South Pole offers none of those advantages. The terrain is ancient, fractured, deeply cratered, and dissected by ridges, scarps, and boulder fields deposited by billions of years of impact gardening. The permanently shadowed craters that contain the ice are, by definition, permanently dark, requiring specialized lighting systems for any surface operations within them. And the extreme low-angle illumination at the poles means that even surfaces outside the permanently shadowed zones are subject to long shadows and short intervals of direct sunlight that complicate navigation and power generation. The Artemis II photographs of the South Polar region, taken from angles and under lighting conditions that orbital cameras, which pass over the poles at regular intervals from predictable positions, don't always capture, will help mission planners evaluate potential landing sites with contextual information that no autonomous orbital survey can fully provide. Northwest of Oriental, the crew observed Hertzsprung Basin, a nearly 400-mile wide impact structure on the far side that represents a different chapter in lunar geological history. Hertzsprung is substantially older than Orientale, and the difference in age is written clearly in its morphology. Where Orientale's concentric mountain rings are geometrically sharp and structurally intact, Hertzsprung's have been eroded and overprinted by 3.8 billion years of subsequent bombardment. The double ring of mountains that defines Hertzsprung's structure is still recognizable, but it's degraded, softened by billions of smaller impacts, interrupted by newer craters that formed on top of the older wound, worn down from alpine sharpness to the rounded, battered profile of genuinely ancient terrain. By observing both basins in a single flyby, one young and relatively well-preserved, one ancient and deeply eroded, scientists gained a sequential snapshot of how impact basins evolve across geological time. The comparison allows researchers to calibrate their models of lunar surface evolution. How quickly do ring structures degrade? How many impacts per billion years are required to produce a specific degree of morphological softening? What does the surface of the early moon have looked like before 3.8 billion years of bombardment had accumulated? On the near side, before the spacecraft swung around the limb to the far side, the crew also documented Glushko Crater, a bright 27-mile wide impact site notable for the brilliant white rays that radiate outward from it across nearly 500 miles of dark mare surface. Those rays are ejecta, material blasted outward from the crater during the original impact event and deposited in long, narrow streaks across the surrounding terrain. Their exceptional brightness tells scientists that the underlying rock, freshly excavated from depth and not yet exposed to significant solar wind processing, reflects substantially more light than the darkened mature surface. By geological standards, Glushko is young. Its rays haven't yet been darkened enough by space weathering to blend into the background. But young in lunar geological time still means somewhere between tens of millions and hundreds of millions of years old. Throughout the observation window, the crew also documented Lobat scarps, low, curved ridges that represent the surface expression of thrust faults formed as the moon's interior cooled and the entire body contracted. Think of a grape drying into a raisin. As the interior volume decreases, the outer crust is subjected to compressional stresses that produce reverse faults. And those faults, where one section of crust rides up over another, create the subtle, sinuous ridges visible on the lunar surface. The Lunar Reconnaissance Orbiter's camera system has identified thousands of these scarps over the past decade, and crucially, their morphological freshness. The absence of the erosional softening that accumulates over hundreds of millions of years suggests that some of them are geologically recent enough that the moon may still be tectonically active, recent enough that moonquakes generated by fault movement could be a real engineering concern for surface infrastructure. The crew's observations of lobate scarps, their three-dimensional relief under low-angle illumination, their relationship to surrounding crater populations, their visual continuity across the surface, added qualitative context to the orbital data that had identified them. 7 hours after the observation window opened, it closed. The crew packed up the Nikons, removed the camera shrouds, and began the long journey home. They carried approximately 10,000 photographs, hours of recorded verbal descriptions, and a collection of observations that scientists at Johnson Space Center are still working through, months after the mission concluded. The flyby did not involve a landing. Nobody walked on the surface. Nobody collected a sample. Nobody planted a flag or drove a rover or spent 3 days on the surface, breathing recycled air and sleeping in a pressurized tent. What the Artemis II crew did was something quieter, more methodical, and in some ways more scientifically consequential. They looked, carefully, systematically, with trained eyes and calibrated instruments, from a proximity and at angles that had never been available to human observers before. They looked at the moon the way a geologist looks at a cliff face, not for the obvious story, but for the details that don't fit. The color that shifts in a direction it shouldn't. The shadow that falls at an angle that implies a structure no photograph had resolved. The flash of light that tells you the surface is under constant, invisible assault from objects you cannot see until they arrive. For 53 years, from the last Apollo mission in December 1972 through the robotic survey campaigns of the 1990s, 2000s, 2010s, and 2020s, we studied the moon through screens. We analyzed it through algorithms. We mapped it with laser altimeters, synthetic aperture radar, gamma-ray spectrometers, and neutron detectors. We built a comprehensive, internally consistent, quantitatively rigorous model of a quiet, predictable, thoroughly understood world. The model was elegant. The model was well supported. The model was a rough draft. The Artemis II crew spent 7 hours demonstrating its incompleteness. The colors are wrong, or at least more complex, more spatially variable, and more geologically informative than orbital spectroscopy had suggested. The topography is more dramatic than any photograph conveys, not because the photographs are bad, but because flat images displayed on flat screens in Earth. Gravity simply cannot communicate the physical reality of standing at a window and watching a mountain range 100 miles high scroll past at 4,000 miles an hour. The surface is being actively reshaped by impacts at a rate that surprised the scientists who had been briefed on impact statistics for years. And one of the most visible features on the near side, a bright swirl you can see from a suburban backyard with a department store telescope, remains an unexplained mystery after 4 centuries of continuous observation. The moon is 240,000 miles away. We have been staring at it since before our species had written language. It shaped our calendars, our mythologies, our navigation systems, our poetry, our understanding of the cosmos. We sent human beings to its surface and brought them safely home. We named every crater and basin and ridge and rill and dome visible through any telescope ever built. We analyzed its rocks in laboratories whose precision would have seemed like science fiction to the scientists who designed the Apollo program. And when 4 people flew out there with cameras and their own eyes, the first thing they noticed was how much we had missed. The photographs are still being processed, nearly 10,000 images, most of them not yet released to the public, awaiting the careful analysis that transforms raw pixels into scientific conclusions. The verbal descriptions the crew transmitted during the flyby are being transcribed and cross-referenced against orbital datasets, LRO imagery, Grail gravity maps, diviner thermal data, to determine which observations correspond to known features and which represent genuinely new information. The impact flash recordings are being matched against lunar reconnaissance orbiter data and citizen science records from telescopes on 6 continents, building a multi-perspective picture of lunar impact activity that will inform the engineering specifications for every crewed structure ever built on the moon. It will take months, possibly years. The full scientific return from 7 hours of human observation will not be known until long after Artemis III has landed its crew on the south polar surface and begun the work of in situ investigation. When that crew arrives, when those first post-Apollo footsteps press into the regolith of the South Pole, they will carry with them every observation, every measurement, every unexpected discovery that the Artemis II crew brought back, not as souvenirs, not as inspiration, as operational intelligence, as survival information. Because the moon that Artemis III will land on is not the museum piece that Apollo described. It is a more complex, more dynamic, more hazardous, and more scientifically rich world than the one we thought we understood for the past half-century. We thought we knew the moon. We had 50 years of data to prove it. Turns out the data was a rough draft, and the real story is only beginning. I hope you enjoyed the video. If you did, please consider hitting that like button. It genuinely helps this channel reach more people who care about the science behind these missions. And if you want to follow this story as it develops, as those 10,000 photographs get processed and analyzed and released, as lunar vertex lands on Reiner Gamma, as Artemis III finally puts boots on the South Pole, subscribe so you don't miss what comes next. The moon has been lying to us for 50 years. I'll be here every time it gets caught.